These are the two convenient tools we use. The behavior of charge. So today we are going to learn a few important things. We are going to revise a little bit, and then we are going to study the various arrangement of charges and their effects. Shall we start? Fine. Children, I want every one of you to keep your video on. It will be convenient for me to track your attendance. Your attendance status. So we learned something that is N into E. We call this as the quantization of the charges. Q is equal to N into E. What do we mean by this statement? Q is equal to N into E. The charges are quantized. What do you mean by charges are quantized? Suppose I have a container, and in this container I have one electron, and I can add one more electron, second electron, then I can add the third electron, fourth electron, go up to n number of electrons. N number of what's the electrons. This electron is just one term to indicate the negative charge. The opposite of the electron could be what's some positive charge. So the value the E is equal to plus or minus 0.6 times 10 raised to minus 19. So what do we call it? What do we call it? We call it a fundamental charge. Fine. So in any, is my voice breaking? Is it better now? Fine. So here we go. So if I have a charged body, in any charged body, the net value of charge Q is equal to N into E. It is the integral multiples of the charges. If this charge is going to be a positive charge, then the E assumes positive sign. If this charge is going to be a negative charge, the E assumes the positive sign and negative sign. They indicate whether the charge is positive or negative charge. And this quantization of the charges, they tell us in any increment or decrement in the charges, if it is going to take place, that increment and decrement is going to take place in a unit value of 1.6. It cannot be any value in between. So it is a discontinuous process. It cannot be a continuous. In case of any raise in the charges, cannot be continuous. So we know that up to certain limit, that is within the microscopic limit, the charge values are integrable. Beyond that, in macroscopic systems, it is not integrable or differentiable either. Fine? Fine, sir. So now this is trying to give me some interest. I have a group of charges. I have a few charges which are grouped in a manner. And what is the strength of the system? How much strength do I get? Because if I accumulate a number of charges, I pick up a lot of charges and I try to accumulate them all, what do I create? I create an electric field source. I have a lot of charges, and those charges altogether electric field. Yeah. So once I create an electric field, what will be the strength of that electric field? We know very well, we have a formula. Strength of an electric field E is equal to 1 by 4 pi epsilon naught and Q divided by R. And in the place of Q, you can substitute N into E. Time, you can substitute N into 1. So this is the equation generally we have, and this equation is applicable for the point source or a point source like system. And we understood something very interesting. Algebraic sum of the fundamental charges. Algebraic sum of the fundamental charges. So I take the fundamental charges and I keep adding them either in a positive way or in a negative way. So altogether, I get a huge picture and I'm getting what's a algebraic sum of all the charges put together. So we have this net value of charge. Much later in time, something very interesting about the behavior of the charges. What is it, sir? If I have 10 charges and I produce an electric field, see for example, I have 10 charges here, 10, 10E, and I put it in a single box and I can try to calculate the electric field strength at a distance of 3 meter. I get a value. Using this formula, I can find a value. Got it? So here I have a lot of charges and using these charges, I can produce a field. This time what I do, I make these charges, of course the 10 charges, but this time I arrange the charges in a random way like this. Then from the center I travel 3 meters and I try to calculate the electric field at this point. Will this electric field in the second case be equal to the strength of electric field in the previous case? We found that the answer is no. These two electric fields will not be equal because we learned one more thing. What is it, sir? The strength of the electric field does not depend only on the number of charges. It also depends on what, sir? Arrangement of charge. And when it of charge, we learned there can be three types of arrangement. What are the three types of arrangement of charges that we can speak of? First one is that are only and connected. This is discrete charge distribution. Under of this the continuous charge distribution. Opposite of the discrete charge distribution is what's a continuous charge distribution. So then continuous charge distribution can be subdivided into multiple categories. What are they? Linear distribution, surface distribution, volumetric distribution. Linear, surface and volume. I hope you remember the formula. That is, formula is charges, that is lambda, which is the charges are kept over a length. And the second one is sigma, which is equal to the charges are kept over an area. And the third one is gamma. Some textbooks are writing this as rho. Whichever is convenient, you can write it in that way. So gamma over a volume. So here the terms area, they are more generic terms. Generic terms. The area and the volume, they depend on the shape that we assume. Whichever the shape that we are going to assume, according to the shape, the area and volume may differ. Got the idea? Can I proceed further? Shall we? So here is the situation. And today I am going to introduce one interesting method of arranging the charge. Interesting method of arranging the charges. Fine. And in all these charge systems, no matter whether it is linear charge system, in all these systems, I want you children to remember we arranged all the like charges. That's the charges which we have taken, all were what? Like charges. This time I am going to take two unlike charges and I am going to combine them. I am going to take what, sir? Two unlike charges and I am going to combine them. So a natural question that should strike your minds that, sir, if I am going to combine two unlike charges, shouldn't they be cancelling out each other? So the net charge of the system can become zero. If the net charge of the system turns to be zero, what will be the net effective field? And the net effective field can become zero. Agreed? Agreed. Then what is the point in talking about taking two opposite charges and combining them? Let's see. I want to ask a question. Answer me. What is this? What is this? Looks like Mickey Mouse, sir. No. This is H2O. We call it a water molecule, H2. Fine. In H2O, the two hydrogen atoms are connected to one O molecule. Fine. Okay. Let's take a big sword and I'm going to cut this molecule into two pieces. I'm going to cut this molecule into what, sir? Two pieces. So let me cut this molecule into like this. This way, let me cut it this way. If I cut this molecule in this way and I observe, the negatives. H is positive, H positive, O negative. I hope you remember chemistry. We have positive rich and the negative rich. So now H2O molecule. Fine, sir. One side is naturally positive, other side is naturally negative. So here the positive and negative charges, they are in equal proportion. They are together, as you can observe. They are together, yet they don't cancel out each other. This is the reason why this molecule naturally has something in it. What is it? Poles in it. Positive poles and negative. That's the reason why you call water a polar molecule. Waters are polar solvents, right? In lower class, you must have studied water is a polar solvent. Why do we call water a polar solvent? Because it has naturally polarity. One side you have positive rich, other side it has what? Negative rich. So this constitutes a perfect system called as a electric dipole system. Pole means two, dipole. Di means two, pole means opposite nature. North pole, south pole. They are two opposite nature. Positive pole, negative pole. Like that, you have a dipole system. Means what, sir? There are two opposite nature which are separated by a small distance. And today's discussion topic, would be electric dipole. Yes. Is my voice breaking? Is it better now or still the same? Suppose if it breaks, let me know in between. Fine. Maybe the connector is loose. Okay. Now can you hear me clearly? Okay. So now let's take electric dipoles. An electric dipole is a method of arranging charges, and these kind of charges they occur in our. We have plenty of dipole systems, HCl, H2O. There are plenty. And these are the combinations of positive and negative charges. So the definition of electric dipole goes this way. Two equal but opposite charges, two equal and opposite charges separated by a very small distance form an electric dipole. Two equal and opposite charges separated by not. The center mass of these two charges should not overlap. So now can you hear me clearly? Or is it too loud? Children, can you hear me now clearly? No distraction now? Oh, fine. Good. Alright, children. Watch this. So electric dipoles are made of two equal and opposite charges separated by a very small distance. So the perfect depiction of an electric dipole would be, let me take a positive charge Q plus and another charge Q minus, and magnitude wise Q plus should be equal to magnitude of Q minus. So under this condition, when the magnitude of Q plus is equal to magnitude of Q minus, and these two charges are taken and they are separated by a very small distance, is called as what's a, they form an electric dipole. So now I am going to draw a line which is going to join their center of masses. So I take the center of mass of charge 1, center of mass of charge 2, and I am going to draw a line which is joining the center of mass of two charges. And we call this line as the axis of the dipole. What do we call this part? This part is called as axis of the dipole. And if you extend this line is called as axial line of the dipole. On either side, if you extend this line is called as axial line of the dipole. So axis of the dipole is found between the two charges, and axial line is the infinite line which is passing through the centers of two charges of a dipole. Noted? Axis of a dipole and axial line of a dipole. Note பண்ணிட்டீங்களா? Proceed பண்ணலாமா? And the distance between the two charges is typically denoted as 2a. Distance is denoted as 2a. The distance between the centers of the two dipoles is denoted with a value of 2 into a. Got it? Fine. And any measurement that we do for a dipole should be taken from the midpoint, called as the neutral point or the midpoint O. So this is the point from where we always do all the measurements. So if we just take this distance, this is A, and this distance, this is also A. So put together the total distance between the two centers is what's a 2A. So we measure. Noted? Fine. And watch this. When we had a point charge, electric field due to a point charge was 1 by 4 pi epsilon naught Q by R square. In scalar form, I am writing all the equations in the scalar form. This is for the point charge. I hope you remember. And second, electric field due to a linear charges, which was equal to 1 by 4 pi epsilon naught 2 lambda divided by R. 2 lambda divided by R. If you take 2 pi, then here it is lambda. Okay? 1 by 4 pi epsilon naught 2 lambda divided by R. I hope you remember this. And the third case, sir. Suppose if you have the electric charges which are arranged over a plane, we had a formula sigma by 2 epsilon naught for a single plate. For two plates, it was sigma by epsilon naught. multiplied by 2. Got it? And then fourth, if the charges are kept over a spherical object, then we had a formula. What's the formula we had? Come on. Once again, 1 by 4 pi epsilon naught q by r squared. We had the same situation repeating again. So in all these equations, we can identify certain things. What are they? The medium factor, strength of the source, and the distance factor. Medium, strength of the source, distance. Medium, strength of the source. This is the only arrangement which is independent of the distance. I think the other day I asked this question. Which arrangement is independent of the distance? Position vector. Instead of asking distance, I asked the term in a technical way, position vector. Got it? So here is the next one. Medium, position or the distance, and the strength of the system. So in each case, the numerators carry, what is it, sir? The strength of the system. So something like that for a dipole system, I need to take the strength of the system. Can I take the Q multiplied by Q? No. In any dipole system, the strength of the dipole system is described by a vector quantity called as P. The P is called as electric dipole moment. Electric dipole. So what is electric dipole moment? Electric dipole moment is a quantity which tells us the strength of this dipole system. நம்ம இந்த பாயிண்ட்ல இருந்து என்ன தெரிஞ்சுக்கணும்? என்கிட்ட 10 சார்ஜ் இருக்குங்கிறதுக்காக அந்த சிஸ்டமுடைய ஸ்ட்ரென்த் எப்பயும் என்னவா இருக்க போறது இல்ல, ஒரே வேல்யூவா இருக்க போறது கிடையாது. Arrangement to arrangement, strength will differ. So in each case, we have different name for that strength. The factor which is describing the strength has different names. In point charge system, it is just the charge. In a linear charge system, it is called as the charge density. It could be linear charge density, surface charge density, or the volume charge density, but it is called as the charge density. Okay. And in the dipole system, it is called as electric dipole moment. Electric dipole moment. அப்போ dipole momentனா என்னன்னு கேட்டா சொல்லணும். Dipole moment is a measure of strength of a dipole. It's a measure of what's a strength of a dipole. Since this dipole moment is a vector quantity, it must have a magnitude and it must have a direction. Am I right? So I'm going to describe the magnitude and direction of an electric dipole moment. So the magnitude of electric dipole moment, magnitude of dipole moment vector is equal to, that is magnitude of dipole moment vector, modulus of P vector is equal to strength of one of the two charges, that is modulus of the two charges. So I'm just writing this as Q without the plus and minus sign. Okay, sir? Strength of the charges multiplied by the distance between them, that is called as dipole's length of the dipole. This is called as the length of dipole. That is what the 2a, right? Length of the dipole 2 into a. So Q into 2a is called as the magnitude of dipole moment. And what's the direction of the dipole moment? Direction of the dipole moment is always from negative to positive. It's always from negative to positive. Okay. So let me re-describe this electric dipole system to you. What is an electric dipole? Electric dipole is a special arrangement of charges. What kind of arrangement are we doing here? We are taking two equal but opposite charges and we are trying to combine them. How are we going to combine them? See, watch this. I have two equal but opposite charges in my hand. I have two equal and opposite charges in my hand. am I going to make the two charges and their center of masses coinciding? No. If I do so, then the first charge will cancel out the second charge. Instead of that, I am going to keep them little bit apart. Little bit apart so that you can connect their center of masses using a line. What do you call the length of the line? We call the length of this line as what's a length of the dipole. We can call that length as what's a length of the dipole. And the midpoint of this length is called as the origin of the dipole from where we do all the measurements. Any distance measurement must be done only from where the origin O. So from that origin towards the right hand side, that is the positive charge, and to the left negative charge, if you travel, what do you call the distance? A. Put together, the net distance is called as what's a 2A. And electric field due to any group of or system of charges is described by three factors: medium, source strength, then the distance. Clear? Medium, source distance, distance and the source strength. These are the three factors which decide. So when I take this special system of arrangement, that is dipole arrangement, in any dipole arrangement, how do I measure the strength of the system? The strength of the system is measured in terms of electric dipole moment. Electric dipole moment, which is denoted with the letter P, small p. Okay? And this dipole moment is a vector quantity. This dipole moment is a vector quantity. Got it, sir? Okay. Now, if I ask you to describe the unit and dimensional formula of dipole moment, can you write the unit and dimensional formula of the dipole moment with already pre-existing information? Dimensional formula. What are the unit and dimensional formulae of electric dipole moment? Just like electric dipole moment, later in time we will study magnetic dipole moment also. Since you can see the dipole moment's magnitude is Coulomb multiplied by 2 distance, that is length. So it is going to be Coulomb meter. Coulomb is the measurement of charges, right? What's the dimensional formula of charges? A into T. And for the length it is L. So it can be rewritten in a proper order. What is it, sir? L power 1, T power 1, A power 1. Yes. Come again. That's right. This A is not area. This A means length, distance. This A is not area. It's okay. It's always good to ask it out. Fine. This A is not area. This A stands for the length. Or you can use the symbol D also. Some people use the distance D also. 2QD also can be used. But as per your textbook, physics textbook, small a is used as describing the length. Okay? Fine. Shall we proceed? Fine, sir. So here we have a dipole system which is described to you. What's a dipole system? Two equal but opposite charges separated by a very small distance. How much is that distance? 2 into A. And this distance should be very, very small. For an ideal dipole, this distance is extremely small. What is so special about the dipoles? Dipoles have their strength described by a quantity called as the dipole moment, which is a vector. Since it's a vector, we need its magnitude and direction. So the magnitude of this vector is 2 into QA or Q into 2A, and direction of this dipole moment is from negative to positive, always. Noted? So now I am going to describe an electric dipole for you. So this is the electric dipole, my plus charge and a minus. A plus charge and a minus charge. Now we are going to calculate the electric field produced by this system. The electric field produced by this system. If you try to draw the diagram of electric field lines for this, earlier we have drawn the electric field line for this kind of system. Can you all practice that once? Electric field lines due to a dipole system? Do it, sir. Electric field lines due to a dipole system. Where is it described in your textbook? Where is it described in your textbook? The picture of electric field lines? If it is old textbook, page number 25. If it is new textbook, page number 20. 20 dana, sir? 21. 21. In old textbook, it is page number 25. And in new textbook, this year's textbook, it is in page number 21. Where you can see this is an important 1 mark question. Generally, they ask you to draw the field line picture of an electric dipole. So Michael Faraday introduced this method to us. By counting the number of field lines in a given area, we can measure the strength of the electric field. And by drawing a tangent at any point, we can calculate, we can determine what is the direction of electric field at that point. So the strength and direction of, that is the magnitude and direction of electric field at any given point due to a dipole can be easily calculated here. Fine, sir. This is old method. This time we are going to use an analytical method to identify it. Got it? So just imagine that around this dipole, I can go anywhere. So here I have plenty of space around the dipole. I can mark a point anywhere. I can mark a point somewhere here. I can mark a point somewhere here, here, here. I can mark a point anywhere around the dipole. At that point, what is the strength of the electric field due to both? This is what I have to calculate. Right or wrong, sir? Right or wrong? So we can do that. It's a very simple task. How do we do that? I am going to use the principle of superposition. I am going to use what's the principle of superposition. How do we do that? Very simple. Watch this. Don't write it. Don't write it. Now, just watch me. So I have a positive charge here and separated by a distance of 2a, I have a negative charge. So let me take a particular point somewhere here. Let me assume a point. And I say that this point, which I have assumed, is at a distance of r1 from the positive charge. And this is at a distance of what, sir? So now let's take, this is going to be the electric field. E due to the first is going to be, because it's a negative charge, or it's a positive charge, so the field is going to be radially outward. And here we have the negative charge, and here radially inward. And this distance is going to be distance R2. So R1 and R2 are the two distances. And these two electric fields, if you separately see the electric field due to the first one and the second one, so if we just mark this point, at this point, electric field 1 vector is in this direction, electric field 2 vector is in this direction. So there is an angular difference between here. So if I ask you to calculate the net value here, how would you calculate? The net E net is equal to root over E1 squared plus E2 squared minus 2 E1 E2 cos theta. Minus 2 E1 E2 cos theta. This is how we calculate. Right or wrong, sir? Agreed? So what's the direction of this electric field? So the direction of the net resultant electric field, direction of the E net is given by, what's the formula, sir? E2 sin theta divided by E1 plus E2 cos theta. E2 sin theta divided by E1 plus E2 cos theta. Got it? So this is very easiest method using which you can calculate. This is what we generally call the superposition principle. What do you mean by superposition? Keeping one over other. What are you keeping over other? You are taking the field due to the first charge, then field due to the second charge, and you are combining. You are keeping one over other. So finally you are getting this. Got it? So now we are going to study. I am going to take two important points as per our syllabus. Very, very important questions there. One of the questions appeared in this year board paper, and definitely this equation which I am going to derive today may appear in your board paper. Got it? Because from this topic there are only two questions which can appear in every competitive examination. That could be this. NEET is no exception. Every competitive exam, no matter you take the BITS Pilani or VIT's entrance exam, SRM's entrance exam, NEET, JEE, regardless of any entrance exam, you will find these questions appearing. Shall we? Yes. So today we are going to study electric field. Give the title, children. Electric field due to or electric field at a point on axial line of an electric dipole. Okay. This is what we are going to derive today. It's a very, very important derivation. I want you children to practice this equation at home multiple times. For us to study this, I am going to take an electric dipole. So one place I am going to take the positive charge, the other one I am going to take negative charge. So let's take a positive and negative charges. Plus charge and a minus charge, which is separated by a distance of from the center to center, line of separation, a minus charge. And I'm going to calculate, suppose if I just extend this line, what do you call this line? This line is called as the axial line. I'm going to mark a random point on this line. At that point, I'm going to calculate what is the strength of electric field. What is the strength of electric field due to these two charges? Can we find? It's a very easy task. Fine. So I am going to mark a point somewhere here. A random point is chosen. Let me call this point as point capital P. I call this point as what's a point capital P. Now I'm going to name this entire system. So the center of the dipole is called as the origin O. From the center, you walk towards the right hand side. This distance is taken as A. Left hand side, you walk. This distance is taken as A. Agreed? Can we proceed? And I told you any measurement that we do, that should be done only from where, sir? Origin, that is center of the dipole. So I am going to take a distance here. This distance is called as the position vector R. Noted? Children, you observe this. According to this picture, the point which I have chosen, according to this picture, the point which I have chosen is lying closer to the positive charge and far away from the negative charge. I could have chosen any point on this line, but my choice of preference is here. You can choose it anywhere. but accordingly your equation should be altered. How it should be altered, I will tell you. I will describe and I will derive this, and I ask you to derive this by keeping the position here. I can ask the test question in any way. Either the point can be kept here or the point can be kept there, and you have to derive it accordingly. So listen to the derivation process very carefully. Got it? So the moment when I choose a point somewhere here, obviously I should understand that the influence of the positive charge at this point should be greater than influence of the negative charge. Why, sir? Because negative charge is at a far away distance, positive charge is at a closer distance. Anyone who is closer, his influence will be greater. It's a logic, basic logic. Suppose if you choose the point there, whose influence should be more? Negative influence should be more. Got it? So we have to consider particular charges, the dominant charge, particular charges, the submissive or the weaker charge here. So according to this picture, who is the dominant, who is the weaker charge? Positive is the dominant charge, negative is the weaker charge. Got it, sir? So the sum is always dominant minus weaker. Formula is always what, sir? Dominant minus weaker. Got it? Let's see. So now let's call these points. The first point is A, second point is B. So at the point A, I have a positive charge. Point B, I have a negative charge. Noted? Any question? Shall we proceed further? If you have drawn the diagram, I'll proceed to the derivation. Children, have you all done? Shall we start? Okay. So the first thing that I'm going to calculate, electric field at point B due to positive charge. Electric field at point P due to positive. The first thing that I'm going to derive. Stage 1. What's the electric field at a point due to point? Very easy, I can easily say. Electric field 1 is equal to 1 by 4 pi epsilon naught. Who is the charge, sir, here? Capital Q. Because it's a scalar form I am writing. So whether I write the positive sign or the negative sign doesn't matter. So capital Q, sorry, small q divided by what, sir? The distance between the positive charge and the point P. What's the distance between the positive charge and point P? It is going to be A P squared. Distance is going to be how much, sir? AP squared. Is that right? How do I write the AP? Because I told all the measurements are taken with respect to the origin. So can I write the AP is equal to, here you can write, here the distance AP is nothing but the net distance R minus the distance A, that will give you the AP. Can you write the AP is equal to OP minus OA? Can you write AP is equal to OP minus OA? So that I can write the distance E1 is equal to 1 by 4 pi epsilon naught Q divided by, come on, sir, R minus A the whole square. Within brackets you have to write along AP, because I am describing the direction also, because this is a positive field. So this positive field should be radially outward field. It should start from A and go towards P. So along AP. Correct? So now I have taken all the information. So let this be equation number 1. Similarly, we can calculate the electric field due to the second charge. So take E at point P due to Q minus. What's the formula, sir, now? E2 is equal to, as usual, 1 by 4 pi epsilon naught Q divided by, the net distance is going to be B to P. Correct? So how do you write the PB here? Very good. Here, PB is equal to P2O plus O2B. PB is equal to P2O plus O2B. This is equal to, sir, R plus. So my equation turns out to be E2 is equal to 1 by 4 pi epsilon naught Q divided by R plus A the whole square. This is along which direction, sir? Along PB, because this is radially inward. Due to the negative charge, should be inward. Along P towards the negative charge. Positive charges have the field away from the charge. Negative charges have the field lines towards the charge. Noted? Can we proceed? So let this be equation number 2. In the second stage, I am going to calculate the net value. So the E net at P. E net at P. Clear? Though I am trying to calculate the electric fields, these two electric field lines are traveling along the same line but opposite to each other. These electric field lines are trying to travel along the same line opposite to each other. What do you call this kind of electric fields or any two vector which are acting along the same line opposite to each other? We have a specific name for that pair. What do we call it? As the E1 and E2 are collinear vectors, coaxial vectors or coaxial vectors. They share the same axis. So they are called as coaxial vectors. Got it? So the E1 and E2 are coaxial vectors. What is the rule for adding or subtracting the coaxial vectors? Just algebraic sum. Combination of a coaxial vector follows what rule? Algebraic sum. Combination of coplanar vector only involves vectorial sum, which you must have studied in your grade 11. As long as the vectors are coaxial, to add them, you can do just algebraic addition. You don't have to involve parallelogram or triangle law of vectors. You just add them like numbers, as long as they are coaxial. If the field lines are coplanar, then you have to use the vectors addition. Got it? So here I am going to say as the E1 and E2, E1 vector and E2 vector as E1 vector and E2 vector are coaxial. The net effective electric field at the point P, E net at the point P. So what do we call it? V at a point on the axial line. So V axial is equal to E axial is equal to, what is it, sir? Electric field due to the first charge minus electric field due to the second charge. Let this be equation number 3. Got it? Why it has to be E1 minus E2, sir? Because they are opposite in nature. So one is trying to push it away, other is trying to pull it in. So I'm just indicating that with the E1 minus E2. Got it? Some people say this is because of the second charge is negative. Kindly don't fall for it. Because in the entire case I am taking what? Only the magnitudes. So I really don't have to worry about the plus sign and minus sign. Here I am talking about who is more effective. And obviously the closer charge is more effective. Closer charge is trying to push the point P away, whereas this charge is trying to pull the point P closer. But who is going to be more powerful here? The fellow who is pushing it away. So I am taking him as the majority, him as minority. Suppose in this entire process, okay, let me elaborate this equation. I am going to substitute the equations 1 and 2 in the equation number 3. So substitute the equations 1 and 2 in equation 3. Substitute equations 1, 2 in equation 3. So by substituting it, I get E on the axial line. E on the axial line is equal to E axial is equal to, come on sir, 1 by 4 by epsilon naught. As 1 by 4 by epsilon naught is common. Let me take it. Of course, Q is also common on the numerator. So let me take Q by 4 by epsilon naught common. And I can take what? 1 by R minus A the whole square minus 1 by R plus A the whole square. Okay. Got it? இப்போ ஒரு சின்ன question கேட்குறேன். Suppose instead of taking the point here, if I had taken the point somewhere here, அந்த equation எப்படி மாறும்? பாயிண்ட் இங்க எடுக்கிறதுக்கு பதிலாக இங்க எடுத்திருந்தா அந்த ஈக்குவேஷன் எப்படி மாடிஃபை பண்ணுவீங்க? E2 minus E. இந்த ஈக்குவேஷன் எப்படி மாறும்? That is 1 by R plus A squared. அப்படியா? இந்த பாயிண்ட் இந்த பக்கம் வந்துருச்சுன்னா அந்த டிஸ்டன்ஸ் குறைஞ்சிடாதா? அப்போ இதே ஈக்குவேஷன் தானே வரும். ஆமாம் தானே? So no matter whether you take the charge at this point or at this point, this equation may vary, but this will remain the same. Because the distances vary. Because for the first charge it is longer, second charge it is shorter. Got it? Noted? Shall we proceed? So now I want you children to cross multiply this. Let me take the Q by 4 by epsilon naught. You take this one here. R plus A the whole square minus R minus A the whole square whole divided by R minus A the whole square into R plus A the whole square. First let me take down this denominator. So can I write this as, I take these two squares away. Can I write this as whole square? Since both are in multiplication, can I write it like this? And this appears to be A plus B into A minus B. Denominator, look at the board children, look at the board, look at the board. So this part is looking like what's our A plus B into A minus B. Correct? So this part can be rewritten as what's that? R squared minus A squared whole power. Correct? So now I want you to use the binomial expansion A plus B the whole squared formula on the numerator and expand. Do it, sir. Work it out. Let everyone do. Done? And cancel out all the odd points, because here we have the plus symbol, here we have the minus symbol. And tell me the final value on the numerator. In exam, you don't have to show this. This expansion part, you don't have to show. If you know the final answer, straight away you can write the final answer. Because the key points are, this carries half mark. This is half mark. This picture is half mark. This carries half mark. This carries half mark. Of course, these are the very important ones along. This is important. These are the keywords. So far, it is 1.5 mark. And this carries half mark. Now we have arrived at 2 marks. And this entire calculation carries just half mark. And the final answer carries half. So how much it is? Half, 1, 1.5, 2, 2.5. Final answer. So totally 3 marks. These are the key terms. So these key points must be present in your answer as per the board exam evaluation. What I generally do is, I use a separate color highlighter. When I study, I use a separate color highlighter. For all the keywords, whichever I study from the first lesson till the 14th lesson, I will use that particular highlighter color for all. It can be a purple color pen, or it can be a brown color pen. There are plenty of color pens that are available today. I use that color pen only when the keyword comes. So when I take a derivation, it will be much convenient for me to identify the keywords. So if I just write only the keywords, I can ensure that I will get the whole mark, total mark in any derivation. Okay, so you children also can follow this trick. Use a particular color pen just to put a box or an underline, so that you can identify those points as the keywords. If that color pen is C, you decide according to you allocate a separate color, but that should be a distinct color. It should not be like the regularly using color. You can buy those pens, 2 or 3 pens, and keep it in your bag all the time. Can we proceed? Yes. So what's the answer on the numerator? The E on the axial line is given by Q divided by 4 pi epsilon naught. Come on, children. This one is going to be 4 times of Q into A divided by R squared minus A squared whole squared. Are you getting it? 4? R. Come again? 4 into R into E. Have you got it? Have you got this answer? So now I'm going to rewrite this 4 as 2 into 2. So if I take the 2Q into A, RB outside, 2Q into A. So what is it? From dipole moment P is equal to Q into 2A, I can write this equation. E on the axial line is equal to 1 by 4 by epsilon naught 2 times of P divided by R squared minus A squared whole square. So this is the formula which we want to. So this is going to be equation number 4. And this carries the half mark. So totally now it is 2.5. Now I'm going to take an ideal dipole, a special case. As you know very well, what's the definition? Okay, once you complete, tell me, I'll tell you the next part. Yes? Come again? On the numerator, yes, on the numerator, 1 hour would be remaining. So let that be. Noted? This is the ideal equation which we need to derive. Now I'm going to take a practical situation here. Watch this derivation. In this entire derivation, I assumed this is a dipole. What is a dipole? Two equal but opposite charges separated by a very small distance. That means this entire distance of 2a should be extremely small. So a should be even smaller than that, half of it. So I am taking a distance r which is much longer. So I take a condition. I call this condition as an ideal dipole condition. An ideal dipole condition. So the special case condition, can I write here, children? Here in this part I write. Okay. For an ideal dipole, for an ideal dipole, r is much greater than a. Therefore, r squared minus a squared is approximately equal to r squared. R squared minus a squared is approximately equal to r squared. Because r is too high, a is absolutely negligible. So r squared minus a squared is approximately equal to what's that? R squared. Because a is too small. Got it? Under this condition, how this equation would vary? We can write the E axial is equal to, come on sir, guide me. E axial is equal to, come on, 1 by 4 by epsilon naught 2 P r divided by r squared the whole square. So I can just write this as r to the power 4. Now I can cross this. I can write the entire answer as E axial is equal to 1 by 4 by epsilon naught 2p divided by r cube. And the most important answer here is along the direction of p vector. Along the direction of p vector. What do you mean by along the direction of p vector, sir? Watch the board, children. Later you can write. Very important thing I'm going to tell you. Watch. The net effective electric field at this point. Who is going to be the dominant charge here? Positive charge. So the positive field is radially outward field. So this is the direction in which E net is going to be. The net effective direction is going to be in this direction. This direction is nothing but the direction of the dipole moment. What's the direction of the dipole moment? From positive to negative. Always the direction of the dipole moment is indicated this way. I hope you remember this. This is going to be the direction of the dipole moment P vector. Is that right? If you observe, the net effective field at this point is in this direction, which is also like the direction of what's a dipole moment. So in the final answer, you mentioned that the axial line, along the axial line, effective field is going to be along the direction of what's a P vector. Got it? Noted? Suppose if you assume you kept the point here, this is the point where you are going to measure the electric field strength. At this point, who is going to be dominant? Negative charge is going to be dominant. And negative charges, they have electric field line in which direction, sir? Towards them, in this direction. This is also in the direction of what? P vector, in this direction. Correct? This is also in this direction. So no matter whether you keep the charge here or here, The net effective field will be always in the direction of what? Dipole moment. So this quantity is always going to be a positive quantity with respect to dipole moment. Got it? Noted, sir? Children, watch now. If I plot a graph, here. Watch the board, sir. Watch the board. If I plot a graph here, along y-axis I have electric field. Along y-axis I have electric field. Along x-axis I have the distance r. And I have two graphs here. Graph 1 marked with the red and graph 2 marked with the green. One is a red graph, other is a green graph. What do they indicate? What do they indicate? Okay, I can take one more also. I can take one more graph here, blue color graph. I have blue, red and green. There are three graphs here. Because they are all three are inversely proportional. Very good. So what are they? Very good, sir. So as you can see, the reduction in the blue is very, very less. So the electric field is inversely proportional to R. For the red, electric field is inversely proportional to R squared. And for the green, electric field is inversely proportional to R cubed. So E by R, that is E is inversely proportional to R, is the case of linear charge distribution due to a wire. So the blue line indicates the source is a line source. The red curve indicates source is a point source or a spherical source. And the green curve indicates the source is a dipole source. So by observing the three different graphs, I can easily identify the nature of my source. Got it? Shall we proceed? Can you proceed? The next derivation we are going to do. Give the title, electric field at a point on equatorial line of a dipole. Sometimes this equatorial line is also called as perpendicular bisector. So last time we saw a line which is joining the two centers is called as what's a axial line of a dipole. Now I am going to show here is a positive charge and here is a negative charge. This is the point O. Suppose if I just split this charge into two equally two halves, Any line that passes through the origin that splits the charge into what, sir? 2. So this line is called as what? Bisector line. It bisects the dipole into 2 equal halves. So this line is called as what, sir? Bisector line. Clear? And this is an oblique bisector line. Oblique means what, sir? Cross manner. Got it? And I'm going to draw a line which is going to be perpendicular bisector. It's a bisector, but still it is going to be perpendicular. Perpendicular to what, sir? The axis of the dipole. And what do you call this perpendicular bisector? This perpendicular bisector is also called as the equatorial line. Equatorial. Got it? Fine. So now your textbook is telling this as equatorial line with a A. I prefer to call this as I. So it indicates the technical name. Later it became equatorial for the equal half. Fine. We call it equiconvex. You remember equiconvex means what? Equally. Can we? So here we have the next derivation. Second derivation is it is electric field at a point on equatorial line of an electric dipole. This is also an important question. This year in board exam also this question appeared in 5-mark segment. Current year board exam this question appeared in 5-mark segment. Every year either this question will come or the axial line will come. Last year axial line came. The year before that equatorial line came. Year before that axial line came. This year axial, equatorial came. So for your batch, it is great chance axial can come. So out of these two questions, one will definitely appear in the board. Got it? So equatorial line of a dipole. What is the strength of electric field? So give some enough space here and draw the dipole here. Give some enough space here and then draw. So I am going to assume a positive charge and negative charge as usual. Positive charge separated by a distance, negative charge. This point is called as O. This distance is A. And this distance is also A. Point is capital A. Point is capital B. Okay. So now what I do? I start from, what's the direction of the dipole moment? The direction of the dipole moment is traveling like this. So let's mark it as B vector A. Mark it in a little manner, very small manner. Noted. So ideally the dipole moment is traveling in this direction. So I am going to take, watch the board children, watch the board. The dipole moment is traveling in this direction and I am going to turn 90 degree away from the direction of the dipole. If I had traveled in the direction of the dipole, I should have traveled like this. But I am taking a deviation of how much? 90 degree because I have to draw a perpendicular bisector. Got it? So I am going to mark a point. So any measurement must be done from where? From the origin. So from the origin, I travel a distance of r. From the origin, I travel a distance of r. In this direction, I travel a distance of r and I mark a point. What do I call the point? Like last time, I call this point as capital P. This is the point where I am going to measure the electric field strength due to this dipole system. And this point P is at a distance of R. It's at a distance of R from the center. Noted? Got it? Yes. As usual, I'm going to calculate the net electric field at this point. Can you do that? It's very easy now. The electric field due to the positive charge at this point, electric field due to the positive charge at this point is going to be an outward field like this. Electric field due to the positive charge, let me mark it as E1. So the distance between the A to P, AP is called as R1. And the electric field due to the second discharge is going to be radially inward. This is E2. This is E1 vector and this is E2 vector. And this distance is called as what, sir? R2. This is R, this is R1, this is R2. Now our diagram is almost over. Almost. Okay. So now we are going to describe a few points and then we proceed. So what are the things that I'm going to write, sir, here as usual? First point I'm going to write is electric field due to the first charge and electric field due to the second charge. Can we write? Yes. Let's write these information. First one is electric field 1 at point B due to Q plus. Electric field 1 at point B due to Q plus. Can you write it? What's the formula, sir? Electric field 1 is equal to 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught. Then, sir. Come again. Into Q by, this is A P squared. That is simply I can write that as R1 squared. It's going to be what, sir? R1 squared. From the Pythagoras theorem, you can write this R1 squared is equal to R squared plus A squared. Got it, sir? This R1 squared is equal to how much, sir? R squared plus A squared from the Pythagoras theorem. If you consider this as a right angle triangle, this R1 squared is equal to nothing but R squared plus A squared. Correct? So from Pythagoras theorem, as I'll write this separately here, as R1 squared is equal to R squared plus A squared. The equation number 1 turns out to be E1 is equal to 1 by 4 pi epsilon naught Q divided by R squared plus A squared. 4 squared வராது ஏன்னா ஏற்கனவே ஸ்கொயர் இருக்குல்ல. கரெக்டா? So let this be equation number. Okay, sir. Distance, direction, sir, along AP. So let this be equation number. Noted. Similarly, can you write for the second charge? E2 at P due to Q minus. So the second one would be electric field 2 at point P due to Q negative. So electric field 2 is going to be 1 by 4 by epsilon naught Q divided by R2 squared. So electric field 2 is equal to 1 by 4 by epsilon naught Q divided by R squared plus A squared again. This time along PB, equation number 2. As you can see, E1 and E2 are equal. As per the equation, E1 and E2 are what, sir? Equal. Got it? But we have a catch. What's the catch? What's the next step? Go back and check. We calculated the first E1, then we calculated the E2. Then what did we do, sir? Go back and check. Go back and check. We calculated the E net. How did we calculate the E net? See that and tell. Of course, we are going to calculate the E net. Yes, sir. Tell me. Yes, sir. Coaxial. Coaxial vectors. So we just did an algebraic sum. But this time, whether the E1 vector and E2 vector, are they coaxial? No. What are they, sir? They are coplanar vectors. So we must use what? Vectorial sum. Got it? So this time our method of addition is not going to be E1 plus E2 or E1 minus E2. This time it is going to be what's a special category addition. What is it? Vectorial addition. So for that, let me first resolve the two components of the E1 and E2 at the point P. So I am going to calculate the effective electric field, at the point P. Can we do that? And do it separately. So at point P, this is the point P, the point P. At this point P, I am going to draw two lines. This is going to be my first electric field line, E1 vector. And this is going to be my second line, E2 vector. So E1 vector and E2 vector are meeting at these 2 points. And you know very well, every vector is resolvable. What do you mean by resolvable, sir? That is, you can easily measure how much do they contribute along x-axis, how much do they contribute along y-axis. What do you call these two? We call them rectangular components of the vector. We call them what, sir? Rectangular components of the vector, which you must have studied in your grade 11. So I am going to split each vector into its x component and y component. Can we do that? So let's take the first vector. The first vector can be divided into E1 horizontal component cos theta and vertical component is here. What is it, sir? E1 sin theta. Divided. Similarly, you can split the second vector along the x-axis E2 cos theta, along the y-axis E2 theta. Got it? So now you can see from the board, watch and watch. Look at the board. From the equations 1 and 2, I can easily identify magnitude wise E1 is equal to E2. Magnitude wise E1 is equal to E2. Right or wrong, sir? Magnitude wise E1 is equal to E2. Only by direction they vary. So if I take the scalar, E1 is equal to E2. Can I write? So can I write as modulus of E1 is equal to modulus of E2, which can be generally taken as E. as per our diagram we can take it. Agreed or not? யாருக்காவது புரியலனா என்னை ஸ்டாப் பண்ணி கேளுங்க. I will teach this part again. Can I proceed? யாருக்காவது டவுட் இருக்கா அதுல? என்ன பாருங்க, இந்த பாயிண்ட் வந்து equally at two distance. As it's a dipole, both the charges are equal and opposite charges. As the charges are equal, the strength should also be equal. Clear? Noted? Fine, sir. So E1 is equal to E2 is equal to E. Under this condition, I am going to take two things. Electric field, effective field along x-axis is given by. Electric field along x-axis is given by. What's the electric field along x-axis, sir? Watch this. E, because E1 is equal to E, so I am just going to write this as E1 cos theta plus E2 cos theta. So the net field along x-axis is equal to E cos theta plus E cos theta. That is going to be 2E cos theta. Equation number 3. Okay. So now let's calculate E along y-axis. E along y-axis is equal to E1 sin theta minus E2 sin theta. Yes, sir, minus. As you can see, E1 sin theta is upward, E2 sin theta is downward. They are in the opposite direction. As you know, E1 is equal to E2. This subtraction should become what, sir? 0. So I can write E along y-axis should be equal to 0. Equation number 4. Got it? So the net effective field at the point P, E at the point P should be equal to net E along X plus net E along Y. Let this be equation number 4. And this field is also known as what, sir? E equatorial, right? So E at the point P is nothing but E along the equatorial line, which is equal to only surviving component is what? Ex axis. Clear? How much is that? 2 times of E cos theta plus 0 na eduthala, sir. I leave it for your understanding. Got it? If you want, you can just write with a pencil somewhere, because we don't have space, enough space. So let this be equation number 6. Noted? Can we proceed? Now, you consider this triangle APO. Consider this triangle APO, and if this is going to be the angular deviation theta, this is going to be the angular deviation theta from this triangle AOP. What can you say, sir? From the triangle AOP, what is cos theta? Cos theta is equal to, come on, sir. Cos theta is equal to, come again, adjacent divided by hypotenuse. That is, adjacent is equal to A divided by hypotenuse should be equal to R1. R1, correct? This. So cos theta is equal to as R1 is equal to as R1 is equal to root of R squared plus A squared. Here. From this calculate R1. From this calculate R1. Okay. Noted. So I can write the cos theta is equal to a divided by r squared plus a squared whole power 1 by 2. I am writing this in the root form. So this is going to be equation number 7. Okay, fine. From the equations 1, 2, we can identify that E is equal to 1 by 4 pi epsilon naught Q by R squared plus A squared. Okay. Now I can substitute the equations 8, 7 in equation number 6. 8, 7 in the equation number 6. You substituted, what do we get, sir? Come on, guide me from here. Electric field on the equatorial line of a dipole is equal to this 2 multiplied by this 1 by 4 pi epsilon naught Q divided by R squared plus A squared multiplied by A divided by substituting the cos theta value. A divided by R squared plus A squared whole power 1 by 2. Got it? On the numerator I have, children look at the board. Children look at the board, everybody please. So 2 into Q into A. What is 2QA, sir? Dipole moment P. So from 2 into Q into A is equal to dipole moment P. E on the equatorial line should be equal to, come on sir, guide me from here. 1 by 4 by epsilon naught. Come on. P divided by R squared plus A squared whole power 3 by 2, because here whole power 1 and here whole power 1 by 2. 1 plus 1 by 2 is equal to 3 by 2. Whole power 3 by 2. Got it? So this is the final answer which we want. What's the formula? Number 9. Got it? And watch, sir. Watch. So here, the effective electric field line E equatorial is going to be, watch the board, everybody. Watch the board. Everyone watch the board. Here, the effective electric field line is in this direction, which is opposite towards the direction of the P. Last time you had what? The effective electric field line was along the direction of dipole moment. But in the case of equatorial line, the effective field line is always going to be against the direction of dipole moment. So if I have to mark it, I have to mark it in a vector form. E equatorial vector is equal to minus of 1 by 4 pi epsilon naught P vector divided by R squared plus A squared whole power 3 by 2. Otherwise, you can just take it P and the P cap. You know, P cap means what's a plus or minus. Got it? This is how your textbook is writing it. So simply you can write this is P opposite happens. Comparing the P vector, this is vector form, this is scalar. This vector form, this time it had extra half mark. So describe the direction of the effective field line. You have to explain. The negative sign indicates that effective field direction at point P, the direction of the electric field at point P is opposite to the direction of dipole moment. Got it? You know the next process. For an effective dipole, yes, very good. Special case. For an effective dipole, right? So what's the next one? For an ideal dipole. For an ideal dipole, what's the condition? R is much bigger than A. Therefore, R squared plus A squared is approximately equal to R squared. R squared plus A squared is approximately equal to R squared. So if you substitute that, the final answer will turn into what's that? E on the equatorial line equal to, for an ideal dipole, sir. What's the formula? 1 by 4 pi epsilon naught. Come on. P divided by R to the power 3. Fine, sir. For R much greater than B. If you want to write it in vector form, how will you write? E equatorial vector is equal to minus of 1 by 4 pi epsilon naught P vector divided by R. That's it. So by comparing the E equatorial and E axial, I can say something. Just look at these two equations. E at a point on the axial line is equal to 1 by 4 pi epsilon naught, magnitude wise alone I'm telling. This is going to be 2p by r cube. And E along the equatorial line is going to be 1 by 4 pi epsilon naught, only the magnitude wise, p by r cube. So I can say E axial is equal to 2 times that of E equatorial. Got it? This is the another relation. So E axial divided by E equatorial should be equal to 2. For the same distance. If you have a dipole, you travel 3 meter along the axial line and you travel 3 meter along the equatorial line, you should get what's a electric field double of each other, right? Along the axial line, the value should be double than along the equatorial line. Noted? Can we proceed? That's it. So for today, we have completed the E along the axial line and E along the equatorial. It's a very important question. Make a note of it. That's it up. Almost your first chapter is over. So we will give a complete revision on the Thursday. Then we will solve the most important problems from this topic on Thursday. Got it? I want Tanishka and Snehita to stay. Fine. Other students can leave, no problem. And Sri Varshini, for you, you have missed a lot of classes. I will give you the compensatory class on the Sunday and I will post the remaining class links to you. You can watch. Okay. Children, sooner I will give you a link for joining the Google Classroom and our app. Already my team has asked for the app team is asking for the name list of students for the admission. I will post that link on the group. By clicking the link, you can join the class. You have to fill the personal information, name, class, and all. Fine. And you have to join the Google Classroom as well as this class. Okay. And I'll follow the link. In 4 or 5 days, I'll post the link to join it. Okay. And other children can leave. Only you two can stay. Bye, children. If you have any doubt, make a note of it and send it to me. Yes. Carry on. Yes, Kanishka, first you. Yes. Do you still feel the need for tuition? Sir is teaching and sir is taking. I think sir has completed the lesson completely. If you feel like, so will you continue here? So can I give your name? Okay, you can discuss with your parents and you post your consent to me. Can I give your name to the app team? Can I? Yes. What about you, Snihita? Sir has started and sir is teaching. I think sir has completed this part. Oh, Revati ma'am. Oh, okay, okay. Okay. So, do you think like you still need the tuition support? So, can I proceed with? Can I give your name to the team? Okay. Fine. Then I will start the registration process for you if it is okay to you. Okay. So you will be officially now on. Will be the students of Chennai Science Academy Physics Group. Okay. Fine, children. Carry on. Carry on.